couple more examples of solving initial value problems that are linear types. So this is a pretty classic type. We have this y prime equals x plus y at ln of 2 is equal to 1. All right. We're actually going to see this differential when we start modeling. But unfortunately for us, we're going to have to solve it at this point by utilizing the separable methods. So, I'm sorry, the linear methods, excuse me. So let's go ahead and write it in the form. Now remember, y prime, we can just say that's dy dx. We're going to subtract y from both sides, and that's going to be equal to x. All right. Remember, we have to solve, or excuse me, we have to define p of x and q of x. P of x is the coefficient of y, which is -1. Q of x is going to be the function on the right-hand side of the independent variable, which is x. The integration factor I, e to the integral of -1 dx, or e to the minus x. All right. And unfortunately, this makes this problem a little bit tougher than the previous. So now what we're going to do is we're going to go ahead and we're going to use our formula. Now, since this is our second time, I'm going to write out the formula one more time. So y is going to be equal to 1 over I integral, well, quantity integral of q of x times I dx plus some constant of integration c. And for this particular problem, y is going to be equal to 1 over e to the minus x quantity integral of x e to the minus x dx plus c. And unfortunately for us, the integral isn't as nice as the previous example. All right, remember that in the previous example it was just a polynomial type, nice and easy. Unfortunately for this one, we can't do a u substitution, we have to use parts. All right? And so we're going to define u to be the polynomial part, x, because we know that when we take the derivative of it, it goes away. And then dv is going to be the e to the x dx. Let's just get the integral taken care of. Let's not worry about anything else that's on the outside for right now, and then we'll stuff it back in when we solve the linear differential. So u is x, dv is e to the minus x dx, du equals dx. Now the antiderivative of e to the minus x, technically, and I just want to make sure that you understand where this comes from, that's going to be e to the minus x. Usually we'd multiply by -1 if it was a chain rule, right? But since we're taking the antiderivative, we're going to divide by -1, right? And again, that only works because the exponent is a linear factor, or linear term, excuse me. If it was an x squared or square root of x, we couldn't do that. And so v is -e to the minus x. Our formula for parts, uv minus integral v du. And so that's going to be x times -e to the negative x, so that's -xe to the minus x, that's uv, minus the integral of v, which is -e to the minus x times du, which is dx. Again, there's that c that's in there. Let's not worry about that until we're done. All right. Now be careful with your signs. This just drops down. We have a negative and negative, which turns into a positive. However, when you take the antiderivative of e to the negative x, that's -e to the minus x. Okay, so it's actually 3 negatives going on in there. Be very careful with your signs when you're doing this. Let's now substitute back into the original solution. In other words, we're going to put that in right here for everything, because now we've evaluated. Right? And if we do that, y is going to be equal to 1 over I, which is e to the minus x. We can just go ahead and drop the solution in. So that's minus x e to the minus x minus e to the minus x plus c. And then we can just multiply through by that 1 over e to the minus x And we're actually going to get a really nice solution, believe it or not, because when we distribute through, 1 over e to the minus x and e to the minus x are going to cancel. E to the minus x and 1 over e to the minus x are going to cancel, so those both become 1s, and then we just get a c over e to the minus x. So I think our nicest looking solution, at least for the general solution, is going to be minus x minus 1 plus c e to the x. And notice that what I did was I just moved that c over e to the x. The negative x became the numerator in this case, or came up to the numerator. So this is our general solution. Of course, we don't want the general solution. We want the particular solution. Y at ln 2 equals 1. Right, so 1 is going to be equal to negative ln 2 minus 1 plus ce to the ln of 2. Right? Now we know that it's e to the ln of 2, that's just going to become a 2, because e's and ln's are inverses of one another. So we're going to get minus ln 2 minus 1 plus 2c. We're going to add 1, we're going to add ln of 2, and we're going to divide by 2. So we could write this as 2 plus ln 2 divided by 2 as our solution for c. All right. And then finally, we just shove that back in, all right, and we wind up with y equals negative x minus 1 plus 2 plus ln 2 over 2 e to the x. Of course, if you don't trust the answer, you can always graph it. All right, and then you want to make sure that it does meet the same conditions on the curve, on the slope field, excuse me, as the solution, the particular solution would suggest. Another example, and this one looks like it's going to be pretty rough, but fortunately for us, it's not going to be all that bad. So we have this dy dx minus cos square x equals negative y tan x. We're going to rewrite it such that dy dx plus y tan of x is going to be equal to cos square of x. All right, so it looks like it's going to be pretty ugly, but it probably won't be, hopefully, maybe. When we go through and try to get our solution, we need a p of x, a q of x, and then we need to get the integration factor. So p of x is going to be tan of x, which we probably don't like already, but that's okay. Q of x, cos square of x. And then finally our integration factor I is going to be e to the integral of tan x dx. Now this is a sneaky one. All right, and this is where you might want to have like that small sheet of integrals that I provided for you, because integral of tan x, to do that by hand is not nice. All right, but fortunately we can just look at it, and this just becomes e to the ln of the absolute of sec x. Notice that x is 0, so we don't even need the absolute value for this because it's non-negative. So we could just say ln of sec x. Right. Or that's just the secant of x. All right. And some of you might not like that too much. Some of you that are looking ahead to the solution might like that a little bit. So our form, one last time, I'm going to write it out. Y equals 1 over I times the quantity of the integral of q of x times I dx plus c. Or that's going to be 1 over sec x times the integral of cos square x times sec x dx plus c. All right. One of the things that we should probably remember is that secant x is just a trigonometric identity for the reciprocal of cosine. And for those of you that foresaw that, you probably really like that, because now we're going to end up with 1 over secant, which is cos of x, times the integral of cos square x times 1 over cos x dx plus c, or, and this is the one we really like, cos x times the integral cos squared divided by cos is just cos x dx plus c. And that's much, much easier to work with. When we integrate cosine, we get sine. So now y as our general solution is going to be cos x on the outside, sine x plus c. Right? So that's a really nice and easy general solution. Didn't have to do parts, didn't have to do a u substitution. We did have to be good with our techniques though, with our algebra as well as our integral. Remember that y at 0 is equal to -1. So by substitution, -1 cos of 0 times sine of 0 plus c. Sine of 0 is 0, cos of 0 is 1, so -1 is equal to 1c or c. And finally, we get a solution. Y is going to be equal to cos x sine x minus 1. All right, so just another example of how to solve something that looks like it's going to be pretty ugly initially by just using this linear technique. All right, we just have one more of these to go through, so we'll do that in a separate video, and then we're going to take a look at the other type of first order that we have to do in this section called an exact equation.